In a groundbreaking revelation that reshapes one of science's longest-standing mysteries, researchers from the University of Oxford have found compelling evidence that Earth's water wasn't delivered by asteroids after all. Instead, the very building blocks of our planet, the same raw materials that fused to form the Earth over 4.5 billion years ago, carried within them the hydrogen needed to create the vast oceans, rivers, and lakes we know today. This discovery doesn't just change the story of how Earth became habitable, it significantly expands the possibility that other planets, too, might be born with everything they need to host life. For decades, the dominant theory suggested that Earth's water was a late arrival, an add-on from space, delivered by icy asteroids and comets slamming into the early Earth. This was a sensible assumption. The type of rock believed to have formed the Earth, known as enstatite chondrite, was thought to be too dry to have produced water on its own. And since much of the evidence for our planet's earliest days is long gone, erased by billions of years of geological activity, scientists have turned to meteorites, the ancient leftovers of planetary formation, as windows into the past. But this new study challenges that long-held assumption in an elegant and exciting way. The researchers examined a rare meteorite, LAR 12252, discovered in Antarctica. What made this particular rock so important is its composition. It closely mirrors the material that would have coalesced to form Earth. By analyzing it using advanced X-ray techniques, specifically X-ray absorption near-edge structure spectroscopy, the researchers were able to peer into the molecular makeup of the meteorite with astonishing precision. And what they found was a revelation. Pockets of the rock were rich in hydrogen sulfide, a clear sign that hydrogen, one of the key components of water, was present in substantial quantities before Earth was even a planet. What makes this even more meaningful is how carefully the researchers ruled out contamination. They focused their analysis on areas of the rock that showed no signs of rust or other damage from Earth's environment. The hydrogen wasn't something that seeped in after the rock landed here. It was baked into its structure from the very beginning. That means the hydrogen was already part of Earth's raw ingredients, suggesting that water wasn't some cosmic accident, but a natural consequence of how Earth was formed. This new insight carries thrilling implications for our understanding of life beyond Earth. If Earth-like planets can form with hydrogen locked inside them, then the conditions for water, and by extension life, could be far more common in the universe than we thought. We may have underestimated the odds. It no longer requires a lucky asteroid collision or a frozen comet crashing into a barren world. Water and life might simply be the logical outcome of rocky planet formation under the right conditions. Dr. James Bryson, a co-author of the study and an associate professor of mineralogy at Oxford, explained that the stable isotopes in the meteorite closely match those in Earth's interior, offering further proof that this wasn't just a fluke or an outlier sample. What they've found is not just evidence of water's origin, it's evidence that our planet may never have been dry at all. Importantly, this discovery doesn't rule out the role of asteroids entirely. We know that some water, especially near the surface, was likely delivered by asteroid impacts, and this new study supports that by placing those events in the right context. But the bulk of Earth's water, especially the water locked deep in the mantle, far below the surface, is far older than those collisions. It's original. It was here before Earth had oceans, before it had an atmosphere, and before it was even fully formed. In other words, water is not a latecomer to the story of life on Earth. It's the prologue, and that reframing opens the door to new scientific questions and explorations. If hydrogen and other essential compounds are intrinsic to the formation of rocky planets like Earth, then maybe Mars, Venus, or countless exoplanets orbiting distant stars had, or still have, the potential to host liquid water beneath their surfaces. It also challenges the criteria scientists use to define habitable zones around stars. If water can emerge from within a planet, rather than being solely reliant on surface temperature and outside sources, then planets farther from their stars, or even orbiting cooler stars, might still have what it takes to support life. This is science at its best, not just answering questions, but transforming the framework in which we ask them. The Oxford team's work is a reminder that even in the most familiar places, like the water we drink every day, there are still deep cosmic mysteries waiting to be unraveled. And sometimes, those answers don't come from deep space, but but from within the rocks beneath our feet. This finding doesn't just add a footnote to the origin story of Earth, it may very well rewrite the opening chapter.